All right, let's dive right in. Today, we're going to talk about something called the axiomatic method. It's this incredible story about a quest for perfect, absolute certainty that, well, took a very dramatic turn. And in the process, it became the invisible engine that powers our entire modern world. So, what is it? At its core, you can think of the method like building with Legos. Seriously, you start with a few incredibly simple, undeniable bricks. Those are your axioms. And from just those few pieces, you start to construct these vast, complex structures of knowledge. The whole point is to build everything on a foundation that's rock solid, not on shaky ground.
I mean, really stop and think about that for a second. What if you could derive everything we know about, say, geometry or even physics from just a handful of truths that are so obvious they can't even be questioned? This was the incredible ambition, the dream that drove mathematicians and philosophers for centuries.
To really get a handle on this, we've got to go back in time. We need to see how this idea grew from its origins in ancient Greece all the way to its absolute peak at the dawn of the 20th century. Okay, so the story really kicks off around 300 B.C.E. with Euclid. This is the guy who built the entire system of geometry we still learn in school today from just a few starting assumptions. Then a little later, Archimedes comes along and shows this isn't just for abstract shapes. No, you can use axioms to explain the real physical world. But then you gotta fast forward over 2,000 years to 1900. A mathematician named David Hilbert proposes the ultimate goal. Let's put all of mathematics on one single perfect axiomatic foundation. And this slide really nails the difference. It just shows you how the scale of the ambition absolutely exploded. We went from creating this beautiful, self-contained system for one single field, geometry, to this breathtaking attempt to capture the entirety of mathematical thought in one flawless logical structure. This was it. This was the dream of absolute certainty. But you know how these grand stories go. There's always a twist. And in this story, that dream of absolute certainty was about to run smack into a wall, a fundamental limit that would completely change how we think about logic and knowledge forever. So Hilbert's big program really had two main goals. The system had to be complete, which means it could, in theory, answer any mathematical question you could possibly ask it. And it had to be consistent, meaning it would never contradict itself. It would never prove that 2 plus 2 is 4 and also 5. It really felt like the final step to making all of mathematics perfectly secure. And then this year happened, 1931. Just let that sink in for a moment. This single year sent a shockwave through the world of logic and math that people are still talking about today. And this is why. A brilliant young logician named Gödel came along and proved that in any powerful axiomatic system, there will always be true statements that you can never actually prove using that system. And if that wasn't enough, he also showed that a system could never prove its own consistency from within. So, just like that, in an instant, Hilbert's dream was shattered. It was impossible. Absolute certainty was off the table. It meant that knowledge wasn't some perfect, finished building, but something that would always have rooms we could never, ever reach. But here's the thing. This wasn't the end of the story. Not even close. The collapse of that dream of absolute truth didn't destroy the axiomatic method. It did something way more interesting. It transformed it. It was reborn not as a path to perfection, but as an incredibly powerful and practical tool. So after Gödel, what did they do? Well, mathematicians basically regrouped. They adopted new foundations, like what we see here, ZFC set theory. They totally understood its limits. They knew it couldn't prove everything, but it was powerful enough and consistent enough to act as the practical foundation for almost all of modern mathematics. The quest for absolute truth was over. The era of pragmatic power had begun. And the whole focus just completely flipped on its head. Instead of trying to build one giant system to prove everything, modern mathematicians started asking a totally different question. What's the absolute minimum we need to get the job done? It's kind of like a minimalist architect asking, what are the fewest, weakest beams I can possibly use to make sure this building stays up? It's a new kind of elegance, one that's all about efficiency and really understanding what's essential. Okay, so this is where this whole abstract historical story connects directly to our lives right now. This reborn, pragmatic, axiomatic method, well, it's the invisible architecture behind so much of the technology that defines the world we live in today. So how does that actually work? Well, computer scientists start by defining axioms. These are the fundamental, unbreakable rules for how a piece of software is supposed to behave. Then they use formal logic to build a system on top of those rules. And this lets them write what's called verifiable code, software that can be mathematically proven to be correct. And that is what leads to the super reliable systems we all depend on for flying planes, for securing bank accounts, for all sorts of critical stuff.
And its influence is it's everywhere. In computer science, you have things like Hoare logic, which gives you the rules to formally prove that software is bug-free. In physics, the Whiteman axioms provide a rigorous foundation for something as mind-bending as quantum field theory. And in AI, specialized logics built from axioms are helping create systems that can make rational decisions in a world that's messy and full of uncertainty.
So, yeah, that grand old dream of a single, perfect system of knowledge, that might be a thing of the past. But what we got in its place is maybe something far more dynamic and useful. A powerful, adaptable tool for building reliable, understandable systems in a really complex world. And that leaves us with a pretty fascinating question, doesn't it? Where are these blueprints of thought going to take us next?